Hi everyone, in this video I'd like to introduce Euler's method for first order linear differential equation. This is used mainly for nonlinear equation. So here's the standard form of the first order differential equation. The right hand side is only in terms of x and y, and there's no y prime in it, and this involves y to the first and y in the denominator. So this is a highly nonlinear equation. So in general, there's no exact way of solving this equation. So we're looking at this numerical approximation of the solution of this first order equation. So here's the basic idea, and suppose this yellow curve is the actual solution of this differential equation. And what we're going to do, starting at this initial condition, so suppose we are looking at not only just differential equation, but we suppose we have an initial condition. So the initial position is here at x equals a, y value is given to b. Instead of computing the actual line, we're going to actually deal with at the moment the straight line, which is tangent to this curve at that point, x equals a. And the motivation behind it is, just realize it's not quite showing everything, so I moved a little bit. So motivation behind it is this y prime. The geometric meaning of this y prime here is the slope of the tangent line. So if I have x and y coordinate at that point, at least we know the slope of the tangent line. So the slope of the tangent line we calculated, and we know the line is passing through. So at that position we can calculate this line. And as I exaggerated in this picture, you can see after you increase your x value a little bit, like this here, by the amount h, which is our usual setup. We want to do this one eventually very small, so that the error introduced after you change your x value a little bit in this part as small as possible. So h is not going to be 0, but something small, so that we can control this one nicely. So instead of this actual curve, we'll replace the solution to this differential equation for the value of x equals a and x equals x1, which will be a plus h here. x1 must be a plus h because it's h increment that is a part of our setup. We replace the actual solution with the straight line, so it is not exact, but it's kind of close and exaggerated here. Again, if h is very small, you can see we're kind of down here. It's very close to the actual curve. Now, we don't know what the solution is, so we're at this position, for example, after we applied our first method using the straight line. So we recalculate the slope here again using this formula. That'll be slightly different slope than this one. And when you're plugging in the x and y coordinate to this one here, all we know is this position, which is not exactly correct position in here. So our slope here is actually now different from actual slope that must be over here. But that's all we got, so we apply our slope formula here at this position, which is a little bit off. So x1 is the x coordinate there, and y1 is whatever that we have a formula that gives us, that we're going to plug in that y coordinate there to get the new slope. And starting from there, we do this again. So we have a slightly different slope that might be slightly different from actual slope and down there. So we continue in that fashion. We have a formula of this on this line and calculate the x and y coordinate of this second point, and plug in those x and y coordinate to the slope formula again and get a new slope. Again, this slope is actually probably different from the actual slope on this actual solution. But we believe if you continue in that fashion with a small quantity of h, it's probably very close to the actual solution. Later in this video, I will show you the computer result of how close these two things are. So on this side here, I'm trying to write down the general formula. If you're in a certain process, in this process, let's say it's xn. So and we have the y coordinate given by zn. So if we have xn, y at zn in here, Then we're going to plug in xn zn into this differential equation and compute the slope of the tangent line at that position and calculate the equation of this line. We call this ln. And using that line and plugging this increment into that line formula, we'll be able to calculate zn plus 1, the next position. And you repeat this process again and again. So it's showing down there. The equation of this line must be in the following form. The slope of this line I call mn. And here's the main variable for this line, x. And x-coordinate of the point the line is passing through is xn. Y-coordinate is zn. So the line must be in that form. This mn is the slope of this line, and we determine that by plugging in xn and zn to this y prime formula. So mn is f of xn comma y zn. So I wrote it down there. I had to reposition a little bit, so it's very tiny. So mn is replaced by f of xn zn. That's the slope there, and this is the main variable. So next part is to predict this value, zn plus 1, using this formula, and xn, and x-coordinate of that point here is xn plus 1. So if you plug in xn plus 1 there, the difference between xn and xn plus 1 is obviously h, and that's our setup. So that's going to change to h, and that's going to be the zn plus 1. So that formula is written in this side. Zn plus 1, that is this part right here. It is the value of this line at the x-coordinate xn plus 1. If you plug it in there, that becomes just h, the difference between these 2 points, h there, and the slope is now replaced by this differential equation formula. So that's how you calculate zn plus 1 from zn, and here's xn zn. F is known formula, h is part of the setup. So how is this h is actually determined? If you're looking at A, that's the initial point. If your target is over there, B somewhere, that's a B. And if you want to divide that into n pieces, 100 pieces for example, then B minus A will be the length of this entire interval of our interest, and divided by the number of intervals you want to divide it, and higher n is going to be more accurate. Then xn, this location is starting from x0, which is our initial position. Here is A, plus every time you go by h, so that's going to be n copies. So that n, unfortunately, this is not the same n. Sorry about the mistake. This better be k, 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 k here, and k times h, and this k, this is n. This is some fixed number at the beginning, 100 number of intervals that you wanted to divide. So this is the idea, and let us use example to illustrate this method, but this is the governing formula of the Euler's method. Alright, the example we're going to look at is not really nonlinear, but we're going to look at this simple example, which is actually linear first order, so we know how to solve it exactly. So we're going to actually solve it exactly and compare this one, the exact solution, with our Euler method solution. Right? The first thing we're going to try, starting from 0, end up at 3. So initial condition is y0 equals 0. That's our just choice to make this example work nicely. And this is differential equation. And we want to predict what happened to y3 using this Euler method. Then this is going to be 3 steps. So we divided 0 and 3 into 3 pieces. Then we can, of course, divide it more, like 100 pieces and 200 pieces using the computer software. We can implement that recursive formula that I showed earlier to repeat that process quickly. So we're going to compare that Euler method with the actual solution we can calculate exactly, so that we can make this comparison. Right, this is our example and the setup. So I copied the computer generated result, and here we're looking at this blue line is actual solution, and we're making the 3 steps starting from 0 to ending at 3. Go about 1 unit each step, and if I use this recursive formula, that Euler's method formula, then first point is still y value 0, and then pick up a little bit and a little bit in here. So that indicates the last value from the Euler's method is a 3, 4. That's the value here. You can see actual value at 3 is quite close to 20. Now this is the image of 10 points. I stick in 10 points in between 0 and 3, and this is the Euler method. And you can see that these points are a little bit closer to the original solution, so what it's predicting, it's more closer and resembles the actual solution over there. So Euler's method predicted at x equals 3, 9.78585. Still far away from actual solution there, which is about 16 something. All right, this is of image of 50 points. When I stick in 50 points, you can see at the beginning it was very, very good. It's almost the same all the way up to like 1.5 is almost the same as the graph, but when it's close to 3, there's a little bit off, and it's predicting is about 14.4. I'm going to increase it to 100, and we'll see how 100 points and see how close this is. All right, this is with 100 points in between 0 and 3, and you can see it's very, very close. Up to like 2 is almost the same curve, and at 3 it's a little bit off. I guess it's by 0.1 or something. Now it's predicting the 15.2. I'm going to increase really to 1,000 points, and I'm sure that's going to be very almost identical curve. Now here's with the 1,000 points that you can see that it's almost the same right here. All right, this is called Euler's method, and there will be the proofs of this Euler's method, why this one is actually converging to the actual solutions.